And this brings us to the law of large numbers. And the weak law of large numbers, you don't have problems as such on that. But what it says is that if you take the average of a sequence of random variables, which all come from the same distribution, then the average will approach the distribution mean. So if x1, x2 from the sequence IID sequence of random variables, so when I say IID, I mean independent and identically distributed random variables with common mean mu, and the distance of this average of these random variables from the mean goes to 0. So the probability that it's away from the mean is 0. So basically it says that this approaches the mean. So the law of large numbers says the average approaches the mean. What the central limit theorem says is what is the deviation of the average from the mean? How is that distributed? If I sort of like blow this up a little bit, this difference is going to 0, but if I try and blow up this difference by, say, square root of n, it approaches some distribution. So let me state the central limit theorem. Basically, if x1, x2, again, we're going to take them to be our IID, with common mean and variance mu and sigma squared. Then, if I look at the sum and I subtract off the mean of the sum, which is n times mu, and I divide by the standard deviation of the sum, which is square root of n times sigma, this is approximately normal 0, 1 distributed as n becomes large. So the larger n is, the better this approximation by the normal distribution.
Maybe asking too much. On the final exam, are you going to tell them that they're IID, or is that something they're going to have to figure out and then?
No, I mean, that is something that, yeah, so it should kind of be obvious that
Right.
they are, I mean, independence, I would definitely state that they're independent. Or, it's like if I say, I'm sampling this, supposing if I say coin tosses, well, you know that they're going to be independent.
Right.
Okay. What's the scenario? If you're not sure about it, ask me about that. Okay. So a problem like this, I don't mind telling you if you're in doubt whether you should assume independence or not. Worst case scenario, you can also just say, I'm assuming that they're independent, and then be done. So when do you use the central limit theorem? When you're given questions involving calculate the probability of
is that sigma times the square root of n? Or is it
yeah, sigma times the square root of n. To multiply. And so if I asked you to calculate a probability like this, get an approximate value for this, approximately, then that's sort of dead giveaway that you need to use the central limit theorem. If say if n was just 2, x1 plus x2, then chances are you could actually figure out what the distribution of x1 plus x2 is and actually calculate the value. But if it's a sum of when n is pretty large, say if n is 10, then instead of actually figuring out what the actual distribution of the sum is, it's better to just use the central limit theorem. Okay. So whenever you see a problem like this where it looks like a sum, n is not a small number where it's trivial to calculate this, then, and also if I say just calculate this approximately, give an approximate value for this probability, then you would need the central limit theorem.
That's what is n large number? N large?
Like any problem where you can't see yourself figuring out the distribution of x1 plus x2 up to xn in the time of the exam. Okay? So I'm guessing if it is more than 2, you probably can't do it. Okay? Well, but I mean, there are situations, of course. Say, if I give you sums of Poisson, you can find that exactly, because you know sums of Poisson are Poisson. If I give you normal, sums of normal are normal. Okay? In that case, then I wouldn't even ask you to find it approximately. I'd ask you to find the probability. Okay? So anything which is non-normalistic, okay, then in that case, first of all, I would state approximately, and then you know, then you can just use central limit theorem. Yeah, so in this class, we're not going to talk about how large n should be to get how accurate an answer, but you will, I'm pretty sure you will know when to use central limit theorem. And as I said, it's basically when it's a problem involving summation and I ask you to only find an approximate value. Now, there are specific applications of central limit theorem when you're approximating binomial or Poisson. Now, it turns out that so basically normal approximation to binomial or Poisson is basically an application of the central limit theorem. And in this case, I can, if y is binomially distributed, okay, and I think I've given you conditions of what n should be, np is greater than or equal to 5, right? Then you can use the normal approximation. Okay, if y is binomially distributed, I can think of y as the sum of n IID binomial 1p distributions. So any binomial random variable is automatically of the form of a summation. So in this case, just for binomial, I can use this approximation too. So if I ask you to find the probability that less than 1 less than b, first thing to do is, since I'm going to use the central limit theorem approximated by normal, and this is discrete, you first do a continuity correction. So you would, that would be corrected term. And then, so a tilde is, say, a minus 0.5, b tilde is b plus 0.5, right, in this problem. And then, the central limit theorem in this case would just be from this u minus np divided by square root of p1 minus p. Let me write as 1 minus np. Minus p. And then at this point you say it's approximately, and that means you've used the normal distribution now. You're assuming this is now normally distributed. So that's for binomial. If y is Poisson and lambda is large, okay. Again, if lambda is greater than or equal to 5, you can take things that to be large. Or, as I said, if I just say find this probability approximately, you use central limit theorem. I mean, you can always use the central limit theorem. The question is, you first of all have to say this is an approximate probability, and the probability is, it may not be a very good approximation. So if I ask you to find the probability of A sample Y less than to B, or just probability of Y less than to B, where Y is Poisson lambda, again, this is just going to be approximately, you do the same thing. You would say Y minus the mean of lambda, which is lambda, divided by standard deviation of lambda, which is square root of lambda, and you would get that this is approximately 5. So the same thing as in binomial. Binomial, the mean that you subtract is NP, the variance is NP1 minus P. For Poisson, the mean is lambda, the variance is also lambda. For any other distribution other than binomial or Poisson, it must be explicitly stated as a sum. Okay? So this here, the sum is sort of implicit. It's implied that Y is actually a sum of Bernoulli's. And if Y is Poisson, it's a sum of Poisson 1 variables. But if it's not binomial or Poisson, then I will actually say that this is going to be the sum of these, some IID random variables. All right. Now, if this number is an integer value, then again we're well, not an integer value, but if my xi's are have a discrete distribution, then for that case too, when I do use the central limit theorem, I need to do a continuity correction. So for binomial Poisson and any other case where it's discrete, you do a continuity correction before you use the central limit theorem. If they're not discrete distributions, then you don't have to bother correcting A by 0.5. All right, that's central limit theorem. Now, this is just one more thing I want to mention, and this is relating to one of the problems, practice problems, and that's because the central limit theorem is often stated in this way. So the way they stated the central limit theorem in the book, they said this quantity is distributed as approximately a standard normal. Another way that this is presented is divide both the numerator and denominator by n. Okay? So if you divide the numerator by n, I get divide this by n, I just get mu. If I divide this by n, I get sigma over square root of n. But basically, I divided both numerator and denominator by n, so this is essentially, these two quantities are essentially the same. Right? So this is the same as this. And sometimes the central limit theorem is stated in terms of this. And they denote this average as, oh, okay, let me write it as this one be different right now. So either I can say the sum minus n times mu divided by the square root of n sigma, or I can say the average minus mu divided by sigma over square root of n. In both cases, what I'm subtracting here is the mean of this quantity. The mean of this quantity is basically just mu. Okay? What I'm dividing is by the standard deviation of this random variable. And in this case, this is the standard deviation of this random variable. Because we did, I think, a problem that said the variance of, it's easy to check this, that's just sigma over n. The standard deviation of sigma over square root of n. So you can see the central limit theorem in this form or in this form. So they're both approximately normal 0, 1 distributed. Okay, that is everything.
Oh,
I mean, that's literally everything.
my head hurts.
I mean, even some things that you may not need, but for the exam, everything. So pick out what you think is important. I've already mentioned some things that I think are important.
When do we get the take-home exam?
Monday. Okay.
Michelle, you said it's the practice problems, right?
Okay, so I'm not going to send out a reminder email that your exam is on Wednesday, but all of you remember, it's on Wednesday, that's April 24th. It's normal class time. So it starts at 4. Well, I think the exam should only take you an hour and a half, but I'll give you the full, whatever it is, 2 hours, whatever.
And what about Monday?
What about Monday? Do you want to have class? You don't want to have class?
Yeah.
Yes.
I'm down.
Yes, to you want to have class?
Yes,
Okay,
yes.
all right, okay.
We could go over the practice problems.
Yeah, okay.
Overall.
We can go with practice problems, yeah. So I tried to write some of the solutions down, but I think it would be quicker if we just worked out all the problems on Monday. Okay. All right. Okay, I need a volunteer if we're going to do evaluation, so you cannot leave yet. Okay. So, I'm going to write this information down.